Hello and welcome back to episode 4 of Calculus 1. I'm Mohammad Momezadeh, the presenter of this lecture. And today we will discuss about one of the preliminary concepts of the calculus, which is the limit. And in this case, we will discuss about the several type of limits, and we will calculate that type of the limits as well. So at the beginning of this lecture, I want to introduce one online platform that sketch the graph of a function, and later on we will use that one to understand the concept of the limits. So this is the online platform that sketch the graph of a function. It's very friendly. You can use it by just writing the function over here. And when we discuss about the function, for instance, y equal to 1 over x, means that for the value of x over here, if we put x as a value that we have it in a horizontal line, then the vertical line, the value on a vertical line determine the y values. So as you can see over here, by moving through the graph of a function, we have several values over here. So you can find the value of the function by just moving the points over the curve of that function. So that's the important thing over here. Let us take a look on the case that we have it. So at the point 1, as you can see, if you put 1 for the value of x, then the y will be 1. But when we moved from the point 1 to the point 0, means that when we move to the 0, as you can see, the value of the function gonna be bigger and bigger, and so on. And when we moved through the x line to the infinity, means that when we tending to infinity, when we approaching to infinity, as you can see, the value of x becomes smaller and smaller. And at the end of the day, over here we have 0.09398, as you can see. And as much as I go forward to the right side, the value of x will be smaller and smaller, but it's never became 0. It's too close to 0, as much as you can see. For instance, at the point 36, 37, we still have the value, the small value for the x, for the y, but that value is not exactly equal to 0. So the concept of the limit is totally related to these things. Means that sometimes you can find the accurate and exact value of the function y. For example, if I consider the point 4 for the value of x over here, y equal to 1 over x, and y is equal to 1 over x, then 1 over 4 or 0.25 will be the value for the given x. Means that if I just put x as 4, the value of y will be 1 over 4 or 0.25. But for some values you cannot determine the things. For example, at the point 0, as you can see, you cannot talk about the value of the function at the point 0. As you can see, you can approach to the point 0, but you cannot evaluate the exact value at that point. Sometimes we have some function that the value at one point is not given. For example, if we consider x minus 1 over x minus 1. So let me just put x over here to have this function. So at the point 1 over here, we have undefined values. As you can see, at the point 1, the function is undefined, but on the other side of the point 1, the value of the function is 1 as well. So by this way we can determine the close values to the point 1 over there. We cannot exactly evaluate the value of this function at the point 1. If you just substitute 1 over here, then we have 0 over 0, which is undefined. The division of a number by 0 is undefined in real numbers, but we can talk about the neighbors of these things. So when we discuss about the neighbors, as you can see, at the point 1 we have undefined value, but close to the point 1 the value of the function is equal to 1. So we can say that the function has a value 1 over there as well. So the concept of the limit is a very important thing, and there are a lot of philosophy about it. You can take a look at the internet and just search about the paradox of a turtle and a shell. There is one paradox that the Russell stated, that type of the paradox about the limits. I'm not going through the philosophy or the concept of the limit like this, but it's not a bad idea to keep it in your mind that what is the meaning of the limit. So let us take a look at one actually graph over here and the slide that we have it. So when we talk about the limit of a function, we just write lim to determine the limit, and we will write the value of a function, for example f of x, where the x tending to some value. So for example, in this case, I want to calculate limit of x, f of x when x tending to infinity. And this f of x over here is determined as 1 over x, so I can rewrite it as a limit of 1 over x where x tending to infinity. The infinity is unreachable value, means that we cannot reach to the infinity, but we can guess about the value of a function at the point infinity. As you saw before on a function that I sketched by that online platform, when x tending to infinity means that x becomes bigger and bigger. So then the happening for 1 over x is given at the table on the right side that you can see over here. So I sketch a table and I put the corresponding values over here. If x equal to 1, f of x or 1 over x is given by 1. But as much as you just grow up the value of x, then f of x or 1 over x becomes smaller and smaller. And as you can see, for the value for 10,000, the value of f of x is 0.00010, and it's totally close to the point 0. So because of that, we can say that the limit of 1 over x when x tending to infinity is equal to what? 0. So that's the case indeed. At the limit, we are not talking about the exact value of the function. The important thing is about the value that we have it in a neighbor, the value that we tending to that one, we are approaching to that value. So we can see that over here x gets larger, 1 over x tends towards 0. As much as you just going through the horizontal line to the positive side, I mean to this side, the value of x becomes larger and larger, and 1 over x, or the value of the function, tends to 0, towards 0. So for this reason we said that the limit of this function when x tending to infinity is equal to 0. So if we want to discuss about the concept of the actually limits, we have the following actually diagram. So one of the important thing is a concept of a limit that we talk about it. So we have the concept of the limit, and the other side is a technique of a limit. So it means that first of all you should understand the concept of limit. As I said, it's about the tending to some values, and the technique of a limit determine the techniques that we can determine the value of a limit. And over here we have the following diagram indeed. So we will discuss about this diagram step by step. So before that, we're going forward and talk about the technique of limits. We need to know something about the right side limit and a left side limit as well. By the graph of a function, that type of the right side and left side limit can be clarified very well. So over here you have a function fx that has two relations. So this type of the functions are given by a different condition for different interval of a real value. So for x less than equal to 2, for x less than equal to 2, the value of the function is given by x squared minus 1, which is a parabola. So we have a parabola over here that is started from this point and ended at the point x equal to 2. So you can see that at the point x equal to 2, the value of the function is given by 2 and 3. Means that if x is equal to 2, you can put that value over here, x equal to 2, then it's consequented, the resulted to f of 2, which is equal to 2 squared minus 1, and 2 squared minus 1 1 is equal to 3, as you can see over there. So means that by the another words, the value of a function at the point 2 is 3. So if we just write it as a ordered pair, then 2 and 3 is a ordered pair that we have it over there. For the different value of x, you can evaluate the value of a function, and the result will be a parabola, something like that, that is ended at the point 2 and 3. For the other side, if x is greater than 2, then we have a linear values, means that y is equal to x plus 3. For instance, if x is equal to 4, you should put the value of x greater than 2, care about it. Then f of 4 will be equal to 4 plus 3, which is equal to 7. So the value for the x greater than 2 should be evaluated by the second condition, which give you the value of 7. And you can see over here that the value of the 4 at this point is equal to 7, means that if you just follow it, we have 4 and 7 here. Right now we want to talk about the limit of fx. We want to talk about the limit of this function fx, where x tending to the point 2, that critical points that we have it here. So the x tending to 2. So what happened over here? How can we calculate the value of a function at the point 2? As you can see, if you go through the value of x where x is greater than 2, means that from a right side of 2, if you tending to the point 2, then the value of a function calculated from here, means that you should calculate the value from the right side of this expression, and at the end of the day the value of y tending to the point 5, as you can see. But if you tending to the value 2 from left side, means that if, for example, we have 1, then 1.2, 1.3, then the value of the function should be calculated over this parabola, and at the end of the day you will reach to the point 2 and 3, or the value of y will be 3. So because of that, we have to split this situation to two parts. One part that we should calculate the limit of this function fx, where x tending to the point 2 from a right side. We denote that situation by x tending to 2 and put the positive sign at the top of the 2. So in this way we determine that we are tending to the point 2 from a right side. So if I tending to the right side to 2, means that x is greater than 2. Over here, when x tending to 2 plus x tending to 2 plus x, if tended to the 2 plus, means that x should be greater than 2. So in this way we should use the second condition over here, means that we should calculate the limit of, instead of f of x, we should put x plus 3, because it's right side of that expression, and x tending to 2 is still tending to 2 plus, and we should put the value of 2 which is greater than 2, I mean the value that is greater than 2. And if I put it over here, the limit value will be equal to 5, as we expected, because as I said it, in a right side of this graph we should move through that straight line to reach to the point 2 when we tending to the 2 from a right side. But when we want to calculate the limit of fx, where x tending to 2 from left side, that we denote the situation by x tending to 2, and we put a negative sign at the top of the point 2, means that 2 we tending to 2 from left side. That means when x tending to 2 from left side, it means that x is smaller than 2. So for the value less than 2, we have this condition for the fx, means that over here, instead of using x plus 3, we should use the x squared minus 1, because x tending to 2 from left side. And as you can see, x tending to 2 from left side reach us to this value. If you substitute the value 2 inside of the equation, then we have 2 squared minus 1, which is equal to 3. And over here, as you can see, the left side limit is equal to 3. And it's clear when we want to tending to the point 2 from left side, means that you should follow the graph of a function over the parabola, and this reach you to the point 3. And as you can see, the right side limit, which is 5, is not as the same as the left side limit. So we said that when the left side and right side limit are not as the same, the limit over there does not exist, and we just denoted by D and E, does not exist. So by the another word, the limit does exist if and only if that the right side limit and left side limit are available and they are equal, so the limit does exist. Over here, limit of fx at the right side, limit of fx at the right side is not as the same as a left side limit, so we can say that this limit does not exist. So I can put it over here that the right side limit over there, so this is the right side limit, is not as the same as the left side limit. They are not as the same. So because they are not as the same, then we can say that the limit does not exist. If these two values are equal, then the limit does exist and it's equal to that value, so the limit does not exist. So this is the concept of a right side and a left side limit, and you can determine it based on a graph that is given over there. But we need to calculate the limit of some function by using some techniques, and for that reason we have the following diagram. If you just take a look at this diagram, we have the case of calculation for a limit. If you want to calculate the limit of a function fx, so for instance, one function is given like fx and the x tending to the a, to the value of a, then the first thing that you should do is substituting that value of a in a fx, means that you should evaluate f of a. So if you find f of a and that f of a has no problem, means that it's not undetermined cases, then you find the limit and everything is good. But you may face with some cases that we call them the undetermined cases. In undetermined cases, we have some type of the fractions or some type of the exponent that is not defined. For instance, 0 over 0. As you know, the number over 0 is not defined. If you have 0 over 0 or infinity over infinity, then we have some type of the undetermined cases. If we have a number over 0, we have the another type of the undetermined cases. Or if we have a number over infinity as well, we have the undetermined cases. And also there are some exponent cases that we have undetermined situations. So for each of these situations, based on that undetermined form, we have some techniques to calculate that in limits. However, these techniques are not covered all cases that you can consider it over here, but at least you have some categorization in your mind. So let us take a look at each of this category one by one and solve some example about that cases as well. So at the beginning of our discussion about the technique of the limits, we just have 3 examples over here. As I said it before, when you have a limit, the first step is substituting the value over there inside of the expression inside of the limit. So for this reason, let us do the same thing. At the first limit, we have limit of this expression, this ratio of the polynomials, where x tending to 1. When x tends towards 1, then we should substitute the value over here, the first step, as I said it. So if I substitute it, instead of the x, I have x squared minus 3 times x, or 3 times 1. Instead of x, I should put the value 1 and plus 2 over the value which is given at the denominator, means that we have x squared plus 1, so we have 1 squared plus 1. As you can see, the value at the numerator becomes 0 and the value at the denominator is equal to 2. So we have 0 over 2, and 0 divided by non-zero numbers will be equal to 0. So we found the limit, and the limit is equal to 0 at the first step. For the second one, we have one trigonometric limit, so x tending to pi over 4. You should keep it in your mind, the table of trigonometric function. As I said it before, to evaluate them, we just put 0, 1, 2, 3, and 4 inside of this table for the x, for the sign of x. Right now we should take roots from it. Roots of 0 is 0, roots of 1 is 1, roots of 2, then roots of 3, and roots of 4 is equal to 2. Then we should divide everything by 2. 0 by 2, 1 over 2, roots of 2 over 2, roots of 3 over 2, and 2 over 2 is equal to 1. So I should replace that last value by 1. Right now, to calculate the value for the cosine, we should interchange their places, means that 1 should be placed at the left, then 0 at the right, and roots of 3 over 2 here, and 1 over 2 at the right side of that one. And we keep roots of 2 over 2 in the middle, means that we have roots of 2 over 2 at the middle. So for the tangent, we should calculate sine over cosine and put it for the tangent of x. 0 over 1 is 0. 1 over 2 over roots of 3 over 2 will be 1 over roots of 3, or roots of 3 over 3 by rationalizing that fraction. And this one is 1, and the next one is roots of 3. Then we have undefined, and because 1 over 0 is not defined, so we should swap their places for the cotangent. So because there is no cotangent here, we don't need to fill the blank places for the cotangent. Right now, x tending to pi over 4 or 45 degree, so we should know the value in that column. So instead of the sine x, I should put the value of sine of 45 degree, or pi over 4, which is roots of 2 over 2. For the cosine also, we have roots of 2 over 2, and for the tangent as well, we have 1. So we found the value indeed. Or you can also simplify it by multiplying the numerator and denominator by 2. If you do that one, then we have the following expression, means that this one by 2 will be this expression. And also you can rationalize this one by multiplying the denominator by the conjugate of roots of 2 plus 2, which is 2 minus roots of 2, and calculate that one as well. But it's enough to just keep it like this. We found the value, and it's determined cases, it's not the cases that we cannot calculate it. The next one is a ln. So if you remember that the ln, or natural logarithm of x, based on that convention that we have, it is defined as a log of x in a base of e, exponential number. And if we have a log of ln of e, or log of e in a base e, then it's easy to see that the value of that one is equal to 1, since e to the power of 1 is equal to e. So that value at the numerator is equal to 1. And at the denominator, we have also e to the power of e plus p, plus pi number over there. So we calculate the value of the limit, because this one is determined cases, there is no 0 at the denominator, or the cases that is undetermined, so we evaluate the limit. So I return back to the diagram that we had it. So if you can substitute the value and the result is a determined form, so you found the limit. But for the undetermined case, we just start our discussion by 0 over 0 or infinity over infinity, and we calculate it for the algebraic cases and trigonometric cases as well. For the algebraic cases, we have two methods of the solving that type of the limit. One is using the algebraic identities or algebraic states that we talked about it in a previous lecture. The another one is using the long division. Let us take a look at some example about this situation. So at this point we are looking at this example, and as you can see we have the undetermined case of 0 over 0 for the algebraic case. As I said it before, the first step to calculate the limit is substituting. At the wasted paper I substitute the value 2 inside of the expression. So we have 2 squared minus 5 times 2 plus 6 that lead us to the 0. So it's not a matter to have a 0 at the numerator, but the problem is about the 0 at the denominator, that we have 2 squared minus 4 that make the denominator 0 as well. So we have the undetermined cases as 0 over 0. So for this reason we should use some methods to avoid the situation of 0 over 0. The important thing over here is about the factor that make the expression 0, and this factor over here should be considered as x minus 2. By the another word, when x tending to a number, then x minus that number means over here x minus 2 is a factor that make the expression 0. So we should factorize this expression out of this limit, and then by cancelling the 0 factor you can solve the limit. So over here I just put three important identity that we use it severally in this case. First of all, there is a quadratic equation. If we have ax squared plus bx plus c, then to calculate that one, to factorize that one, we will write it as 1 over a, open the bracket, ax plus alpha, and the another bracket is ax plus beta. So what is that alpha and beta? The alpha and beta is calculated such that the addition of alpha and beta is equal to b, these elements at the middle, this constant at the middle, and alpha times beta is as the same as a times c. So this relation help you to factorize the quadratic equations or the equation of a second degree. For instance, if you have 3x squared minus 2x minus 1, over here a is 3, b is minus 2, and c is equal to minus 1. Then to factorize that expression, I will write 1 over 3 outside of that bracket, and inside of the bracket I just open the bracket, and inside I will write 3x and 3x. Then I'm looking for two numbers alpha and beta such that the addition of alpha and beta is equal to minus 2, or the value that we have it as a constant over here, and alpha times beta should be equal to minus 3, the multiplication of this 3 and this minus 1 as a constant part over there. So if you just take a look over here, this alpha and times beta will be equal to minus 3. This minus 3 can be written as 3 times minus 1 minus 3 times 1 and so on. But I'm looking for a case that the addition of these two numbers is equal to minus 2. The only case is this case, that the minus 3 and 1, their addition is minus 2 and their multiplication is minus 3. So I replace it over here, minus 3 and plus 1, and then I factorize that quadratic equation indeed in this way. So the another type of the identity that we should consider it over here is a conjugate identity. When we have x squared minus a squared, then you can factorize it as x minus a times x plus a. Even if the number is not complete square, like 5, then you can rewrite it as a roots of 5 totally square, and you can split it like this: x minus roots of 5 times x plus roots of 5. The another type of the identity that is used severally over here is x cubed minus a cubed. That can be written as x minus a times x squared plus ax plus a squared. And we have an example over here that you can see that how can we split x cubed minus 1 to two brackets or factorize it to some factors. So over here we have 0 over 0, and we should use some methods to split that actually expression and take out the factor that make the expression 0. So x tending to 2, we will write it over here, and for x squared minus 5x plus 6, I will open the bracket because the coefficient of x squared is 1. No needs to put any number outside of these brackets, and inside of the bracket simply you will write x. Right now I'm looking for two numbers that their multiplication is 6 times 1. I just multiply the coefficient of x squared by constant. Their multiplication is 6 then, so means that alpha times beta over here is equal to 6, and moreover the addition of alpha and beta is given, means that alpha plus beta is given by minus 5. So we have several cases for that alpha and beta that their multiplication is equal to 6. For example, 2 times 3, you can rewrite that one as 2 times 3, you can rewrite it as 6 times 1, and also 6 times 1, you can write that one as, let me just consider it 2 better than that. So you can make it also minus 2 and minus 3. You can calculate that one as actually minus 6 and minus 1, but their addition should be equal to the constant part coefficient of x, which is minus 5, not 5. So the number that we can find it is minus 2 and minus 3. So I will rewrite over here minus 2 and minus 3 for sure, because we have a zero factor. X minus 2 should be found over there. The another thing is about the denominator, that you can apply the conjugate state and write it as a x minus 2 times x plus 2. Over here always you should find a factor of x minus a, and by simplifying that expression, this part can be simplified inside of that limit, and right now this factor is eliminated. Right now just replace x by 2, then we have 2 minus 3 at the numerator, and at the denominator we have 2 plus 2, which is 4. So if you just calculate that one, 2 minus 3 is minus 1 over 4, give you minus 0.25 or minus a quarter. So this is the method of solving undetermined 0 over 0 for the algebraic case. The another method is using the long division. Let us solve one more with the long division now. So we have the another example over here that you can substitute the value over here and find out that the expression is 0 over 0. I will avoid to write it over here and calculate it, but it's simply substituting x by minus 1, and you will find the case of 0 over 0. But over here at the numerator, as you can see, we have x to the power of 4, and based on the identity that we discussed about it before, it's not easy to find that factorization over here and use that factorization method. However, there are some methods that you can use it, but over here we prefer to use the long division to calculate that things. How can we apply the long division? So when we have the limit of some function, limit of fx over gx, for example, and we want to and we face with the case of the undetermined case of 0 over 0 where x tending to a, then we just divide fx and gx by x minus a. X minus a is a factor that make the expression 0, so we should divide both of them by x minus a. We should do the same thing over here. So let us take a look at this expression that we have it for x4 minus 3x minus x plus 1. As you know over here, x tending to minus 1, so we just rewrite that expression, and that exponent should be transcendental, means that the powers should be decreased. The first one is 4, then 2, then 1, then 0. So if it's not, you should make it on that case. Then I just sketch the division sign, and I should divide it by x minus a over here, and x minus a, the a over here is minus 1, give us x plus 1. Care about it that the factor over here is x plus 1, so I should divide this expression by x plus 1. And if I divide it by x plus 1, means that I should use the biggest or greatest exponent first. It is x4, and I should divide it by the biggest exponent of a divisor, which is x. x4 over x give us the x cube, so I should divide that one by x cube. Right now I should multiply x cube by x plus 1. It's give us x to the power of 4 for the first case, plus x cube. So right now I should change the sign of this expression. That plus should be changed to the minus, the second plus also should change to the minus. Right now x4 and minus x4 will be cancelled, then I have minus x cubed as a expression that is remained over there, and minus 3x squared minus x plus 1, up to the time that the degree at the remainder is bigger than the divisor. You should continue the division. So the next one is dividing minus x cubed by x, which give you the minus x squared. If you just multiply this expression by minus x squared, then we have minus x cubed minus x squared. So right now I should change the sign again. If I change the sign and change the minus to the plus, then by adding this expression, minus x cubed and plus x cubed will be cancelled. Plus x squared minus 3x squared give you minus 2x squared. So we have minus 2x squared minus x plus 1, and we should continue our division by dividing minus 2x squared by x, which give you the minus 2x. So if you just put minus 2x over here, then the multiplication give you minus 2x squared, the first multiplication. The second one is minus 2x times 1, which give you the minus 2x. So right now again I should change the sign of this expression over here. If I change it, this minus becomes plus and this minus as well. So right now 2x squared will be cancelled from the expression, and 2x minus x will give you x, and 1 is coming in a remainder. Right now you should divide x by x, which is equal to 1. So I just do the same thing, and 1 times x plus 1 give you x plus 1. And again you should change the sign of the result over here, which is minus x minus 1, and after cancelling this expression you will find out the remainder will be 0. Always in this situation your remainder should be equal to 0, otherwise you made a mistake in some part of your long division. So right now I can rewrite that limit as follow, means that this limit can be rewritten again as limit of x tending to minus 1. It's not change anything else up to here. Then instead of the terms at the numerator, I can rewrite this multiplication, x plus 1 times this expression that you find it over here. So means that I can rewrite that one as x plus 1 multiplied by the terms that we find it by dividing that things, means that we have x cubed minus x squared minus 2x plus 1. So we just write it over here that it's minus 2x plus 1, and at the denominator as well you can use the conjugate state simply. So if you just use the conjugate state, it will be x minus 1 times x plus 1. And right now the factor that make the expression 0 can be cancelled over here. X plus 1 from a denominator and numerator will be cancelled. Then substitute the minus 1 instead of the x over there. If you just do that one, the first one minus 1 cube will be minus 1, then we have minus 1 squared, which is minus 1 again, then we have plus 2 for minus 2x and plus 1 as well. So the result is 1, and at the denominator we have minus 1 minus 1, so we have 1 at the end over 2, minus 1 over 2 indeed. So we just solved the equation over here by using the long division. I hope that you understood the concept. The another type of 0 over 0 is the trigonometric cases that you should use the trigonometric substitution. I will give you one example from that case as well. So as you can see in this example, we have limit of tangent x over cosine x minus 1 when x tending to 0. And as you know, the tangent of 0 is 0 and cosine of 0 is equal to 1. So by substituting the value on the limit, then you will reach to the case of 0 over 0. So over here we will use these two identities only. I mean, we just need these two identities, that the tangent is sine over cosine and sine square plus cosine square is equal to 1. However, you may face with the other types of the identities when you want to calculate that type of the limits. So it's necessary to memorize all of that identity and keep it in your mind to calculate the given actually cases. So to calculate that limit, I just take a look at the denominator of that one, which is cosine x minus 1, and it's remind me that the 1 is sine square plus cosine square, but over here we have cosine of x only. So to make that one as a cosine square, I just multiply that expression and divide by the same terms. That is a conjugate of cosine x minus 1, means that instead of the minus, I will convert that minus sign to the plus sign. In this way I can use the conjugate state as well. So means that I divide this expression by cosine of x plus 1 and multiply the terms by cosine of x plus 1. Then I can reach to this actually things, means that it will be equal to the limit of x tending to 0 again. But at the numerator we have the same thing, means that at the numerator we have tangent of x and tangent of x multiplied by cosine x plus 1. It's not change anything else. Let me just put the 1 at the left side to avoid any problem to misunderstood that expression. So at the denominator we have cosine square of x, because it will be x minus a minus b times a plus v. The first one is square minus the second one is square, which is 1. And based on this one, cosine square minus 1, if I shift 1 to the left side, will be minus sine square. Just shift sine to the right side and 1 to the left side, then you will find that the cosine square minus 1 is as the same as minus sine square. So the limit is changed to this case indeed, that we have limit of actually x tending to 0, and at the denominator by this actually calculation we reach to the minus sine square of x. Let me just change that tangent to the tangent square to avoid the problem to have 0 again at the denominator, because otherwise you should apply the another methods as well. So I will change the question to the tangent square. Right now the tangent square as well can be written as a sine square over cosine square, sine square of x over cosine square of x. And we still have the terms of 1 plus cosine of x at the numerator. So right now this sine square will be eliminated from the numerator and denominator, means that this factor will be eliminated, and right now substitute the value. So if you put x equal to 0, then we have 1 over 1 square, cosine of 0 is 1, and 1 plus 1, 1 plus 1, and at the denominator we have minus 1. So it will be 2, it will be 2 over minus 1, or the result is minus 2 as well. So as I said it, we can modify this question and prepare the different type of the identities for the trigonometric function, and for each case you should apply one suitable formula, suitable algebraic identities to calculate that type of the limit. And it's not only one case that you solve that type of the identity by one type of the models. So as much as you solve more examples and just be familiar with more identities and keep all of them in your mind, you get expert in this type of the things as well. So in the next case actually we have the another type of the 0 and 0 over 0 that we can solve it by Hospital rule. But the Hospital rule should be considered after the derivative, because we need to know how to calculate the derivative. So for that case we just skip from the Hospital rule and we keep that model or that type of the solution. After that we discuss about the derivative. It's a part of the application of a derivative later on. So if we return back to our diagram, we just talk about the first branch of this diagram, means that we talk about the algebraic ratio, that we should use the algebraic identity, or using the long division, or trigonometric function, that you should apply the trigonometric identities. The Hospital rules also should be considered after the discussion of derivative. So right now, in the next lecture, we will discuss about the case that we have an infinity over 0, or infinity or number over 0, or number over infinity, and also the infinity over infinity should be considered, and we will solve some cases of infinity over infinity as well, and remain parts as well in the next lecture. So thank you for attending this lecture, and I hope that you understood the concept of our discussion today.